there's this phenomenon known as photorespiration where Rubisco, so normally Rubisco does this Calvin cycle. And that's the classic thing that we like to talk about for photosynthesis, is that's how we get our 6 carbon sugars, our glucose. But Rubisco actually has 2 competing pathways. One is a carboxylation pathway, and the other is an oxidation pathway, where instead of adding CO2, ribulose 1,5-bisphosphate can be attacked by oxygen, okay? O2, it can react, and then we get this glycolate. Okay, so a 2-carbon molecule. Well, this isn't productive, right? Because we're not fixing any CO2. Actually, this is an unproductive pathway. And what the photosynthetic organism usually does is tries to recycle those 2 carbon sugars by passing them from the chloroplast to the peroxisome through some carbon intermediates in the mitochondria, and then it converts glycine into serine in the mitochondria and then shuttles it back up through to the chloroplast back as a 3-carbon molecule. So it tries to recycle these 2 carbon molecules back up into the chloroplast to enter the Calvin cycle as a 3-carbon molecule. So there are 2 reactivities for Rubisco. It actually has both a carboxylation, a productive pathway, and then an oxidase or an oxygenation pathway here that is unproductive. And it just breaks it in 2 into a 3-carbon and a 2-carbon molecule. And that's one of the reasons that plants actually have lower yields, because some of the energy that was absorbed in light is lost because now we're oxygenating our substrate here instead of carboxylating it, which would be productive. So this process that we went over in class was the photorespiration pathway. And I put the C4 cycle here. And all that I talked about with the C4 cycle is this little tiny bit here. Some plants actually try to counter this oxygen pathway by increasing the amount of carbon dioxide in the chloroplast. Okay, so the C4 cycle, okay, and I'll show it in a second, is a method for increasing CO2 concentrations in the chloroplast, because these are competing pathways, right? The enzyme could take oxygen, the enzyme could take CO2. So which one wins out? The one with the highest, right, amount and the lowest Km value, right? So what plants have is they have an apparatus that will fix or actually increase the amount of CO2 in the chloroplast. Okay? So, hello. So I didn't show it because I didn't want that to be the main point. I wanted you to know the carboxylation reaction. But what they do, okay, that's why it's not there, is this is actually the C4 cycle. So you can see here's the stroma. We can see here this mesophyll structure and these different subcellular structures, these bundles of sheaths, these veins where the water and things come up through. And the C4 cycle is a way to sequester carbon dioxide from the air. And what you do is you fix it into a carbon-4 molecule. Okay? So this is PEP carboxylase. And what we have here is a cycle, the C4 cycle, that will take phosphenylpyruvate, we saw it in glycolysis, okay? But instead of making pyruvate, we take phosphenylpyruvate, and then we attach a CO2 to make a carboxylic acid on there directly, bypassing basically the formation of pyruvate. And then what happens is you'll take oxaloacetate, this is our carbon-4 molecule, make malate, and then it will send malate into this bundle sheath right here next to the chloroplast. See the bundle sheath right here? It's right next to the chloroplast. And what will happen is once it gets into that bundle sheath cell, it will decarboxylate it. And then what happens here is it's right next to the chloroplast, so that will diffuse and locally increase the concentration of CO2. So that it will outcompete the oxygen. So the C4 cycle here is a way to boost the carbon dioxide concentration in the chloroplast. Okay? So that CO2 concentrations will be greater than the oxygen concentrations in the chloroplast. So the C4 cycle is a cycle to sequester CO2, fix it, so that it can basically deliver that as CO2 in the chloroplast where it does the dark reactions. And it increases the amount of CO2 so that Rubisco will prefer CO2. So that's what that C4 cycle is. You don't have to know that reaction. It's already intermediates that you're well aware of from glycolysis, right? And from the citric acid cycle. So, but that's all it is. It's a way of, we got this problem, there's a competing pathway, oxygen, carbon dioxide, and depending on which one's present in the most abundance, it's going to dictate what Rubisco will do. By doing this C4 pathway, we can locally increase CO2 concentrations in the chloroplast by doing this reaction. So it costs something though, it costs ATP. So it is, it costs energy to do this. But that energy is used to increase the CO2 concentrations, but this is why crop yields are actually lower than what they could be, because some energy is used to concentrate CO2 so that Rubisco will prefer to do the CO2 carboxylation reaction. Does that make sense? Okay. So I didn't go over that in class because I thought we already had enough reactions to go, but that's what it is. It's a pretty straightforward. Everything you've already seen. Okay. So that was one thing that someone wanted me to go over and discuss. The other thing, was coenzyme Q, which we can discuss as we talk about photosynthesis. So to break it down, what are the key things that we have here? And if somebody has any questions, I'll just we have chapter 15, which is photosynthesis, okay? And we can break that down into the two reactions. Light reactions, dark reactions, regulation. That's kind of a summary of all we went over. And then chapter 16. We didn't have anything from chapter 14, did we? Left over? I don't think so. Chapter 16 was fatty acid degradation, and we can think of, saturated and unsaturated, those were the main things, and then transport. Of fats, cholesterol. And we already talked about those molecules, in chapter 11, I think, 10 or 11. So those were the main things that we covered. let's just go through the different reactions. And then is there anything in particular you want me to go over that was like, yes?
Can you go over the beta oxidation of polyunsaturated?
Yes, polyunsaturated fats. So we'll start with fatty acid degradation. Let me go to a new slide. So we're going to start here with our fatty acid. So, and I like to do palmitate. That's what everybody usually focuses on because that's the most well understood. Study 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And I'm just going to put C16. And up here is C1. Okay? In order to actually start this degradation, the first thing we have to do is activate it, right? So, first thing we're going to do is attach AMP to it to activate it. So we bring in ATP. And we send out our pyrophosphate. And I'm fine with you just putting AMP. I think you don't know the structure now. Okay, so AMP, AR16. If you all want to, I'm okay with you doing like 1, 2. Okay. You can do this if you want. So we have 1, 2, and then we would need what? 2 up, and then there's a third one here, and so 15, or not, 13. You can do this if you want. You guys okay with that? If you want to do that, or you can draw it out as the long tail, because it's pretty much the same. Actually, to make it so that you can do the chemistry, just a second, because you have to see the beta oxidation. Here's how I would do it. 1, 2, so there's alpha, beta, and then after that, you can put that there. Okay. So 1, 2, 3, and we need 13 more. So that's how I would do it, and that way you guys can keep track. You don't have to draw out so much. So that should add up to 16, right? 12, 13, 14, 15, 16. And what we're just saying is you repeat that. But I like this to be here so that you can see, because we have to oxidize that position, right? So that's the first thing we do. Now we have to activate it and get coenzyme A attached to make our thioester. So we bring in coenzyme A. AMP leaves. Again, you're breaking. This is energetically favorable because you've installed now this activated bond, and a thioester has about the same energy as a phosphodiester. So we would make CoA. And I like to put this S there so that you know it's a sulfur. Do it. Okay. So now we have our activated molecule, and of course this will be transported in to the mitochondria using the carnitine system. This is all happening outside here in the cytosol. Okay. This will then get transported into the mitochondria via the carnitine transport system. Membrane, we're going to transport it in. Okay. And here's our mitochondria. Okay. So then, once we get it in here, we're gonna do a process of beta oxidation. That comes in here. First step is an FAD dependent enzyme, dehydrogenase. Just need to know the kind, you don't need to know the base or the substrate name for it. We get FADH2, and what it's going to do is it's going to take two hydrogen atoms, one from each carbon here. And then we'll get a double bond. Like that. Okay. The next step is we need to, so we've oxidized this partially, we've stolen electrons away from it. And right, this can be shuttled to the electron transport chain. Remember that? There's a mediation process and it's can be transferred into the electron transport chain. Okay. Now we can actually oxidize this further. This becomes electrophilic, and we can bring in water, act as a nucleophile, because remember this is in conjugation with a carbonyl. So that beta position, alpha, beta. Okay. Now we can bring in oxygen at that beta position. H2O. Then we're just going to oxidize this further. There's only 4 steps. But we're going to bring in NAD plus. We're going to get NADH out. And then the last step is we're going to use a thiolase. Now that we've installed this beta ketoase, well, it's not an acid at this point, but this beta keto molecule, acyl group. Now this is reactive, and so we're going to bring in another coenzyme A, and the enzyme thiolase. Okay. This is a hydratase. This is a dehydrogenase. This one will be called thiolase, which brings in another coenzyme A. And here's how I'll draw this. I'll just have it knocking off an acetyl-CoA group. Over here. That comes off, and then what we're left with is so we just chucked off 2, so we should have 10, and then now we have another position here, and we can just send that on back through, so we can think about this being sent up back through there to that enzyme, that dehydrogenase enzyme. So pretty straightforward. Probably one of the easier, I think, pathways we've done. Okay, but then it gets complicated. Then we start putting in unsaturated, right, components. Is everybody good with that part? And that's how you can draw it out. I'm fine with you abbreviating it that way, and that actually allows you to see it better. You know, I'll just take a look. So how many times will we have to run this back through to completely degrade this down? Do 5 or 4? Because on the last one, remember the final one, you have 4. They each get split into acetylcholine. So, oh yeah, we have 12. You're right, 5. Yep. We still have 1, 2, 3, 1, 5. 5. Actually 6, because there's 14 left. So whatever you do, you take, okay, however many is there, there's 14 left, okay? 14 divided by 2 is 7 minus 1, because on the final step, you get 2 acetylcholine. So that's how you can do it. So there's 14 carbons here, 1, 2, 3, 4, and then 10 is 14. Divide it by 2, minus 1. That's how you know how many more cycles. Because on the last step, you cut them into 2 acetylcholine, and there's no more. Okay, so that's that. Now let's look at unsaturated fatty acids. And this is all happening in the same way, same place. I'm just going to draw out, you still have to activate it. I'm going to bypass the activation, and we're just going to look at the cycle. So we're going to start out up here. And I will draw it out this time just so you can see, remember, unsaturated fatty acids always start at delta 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And then I'm going to make this a polyunsaturated just for here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we'll just make it 16 when it's polyunsaturated. Now you've seen how we've already done that, and so what you would look at this and say, well, it's going to cut off 2 at a time, and it will treat everything up front just like a normal saturated fatty acid. So it'll cut off 2, 3, 4, okay. And then once it gets here, we'll get to a problem. So I'm just going to summarize this. It's everything that we've done. We're just going to say that it's going to do 3 rounds of beta oxidation steps 1 through 3. And basically everything would be the same there. So I'm going to draw it over here, what we would get by that time. So, just to show you, okay, this carbon here correlates to this carbon here, and here's array S. So I'm arranging these, and then what will we have? We have this. Okay. So all that would be the same. That's what we just already went through. Then we get here, and what we would like to do, right, is we would have liked to taken the alpha and the beta carbon. Here's our alpha, here's our beta. And we would like to reduce that, or oxidize it, I'm sorry, with step 1. But we have a problem. I'm just going to mark this alpha, beta, gamma. But we can't do that because then you would be trying to make a double bond next to a double bond, that just isn't going to work. But there's an enzyme that allows you to flip this. It's an isomerase, right? It's just going to make an isomer of this, where it's going to effectively just flip the double bond over here. Okay. So we use the isomerase. In isomerase reactions, we've seen those, about 4 or 5 kilojoules per mole, delta G naught prime, right? So this is the one that can easily be done based off of concentration. So then what do we get? So there's our alpha, beta, gamma. Double bond would be. Let me write Charles up. One carbon. 1, 2, 1, 2. Kind of flips it around a little bit. Does that look like the right number of carbons? Looks good to me. But because now we get that trans bond in there, it looks a little bit different. Okay, so we treat that the same way. We use an isomerase that's just flipping around, your hydrogen atoms. And so this is really just bypassing step 1. Bypass step 1, because we already have that degree of unsaturation. And then now we just do, your normal, you go to step 2, so we'll bring in water. Well, then what do? We're going to now oxidize that further. And then we're going to use our bioreactor. So this would be step 2, 3. Would clip off the acetyl group. So we get to here. Okay, this is where I kind of flubbed on the initial one that I went through. Okay. We can now do beta oxidation here, right? It's perfectly fine. Here's our alpha, here's our beta. We can do step 1 and install a double bond there. That's what we'll do. We'll go back through and we'll do step 1. FAD. FADH2. And then we get this. Let me fix it so it's nice and straight. So I'm trying to arrange this so that everything's lining up. So this carbon's here, this carbon's here, and here's our double bond, and then those are the final ones. Now what's happened is, okay, yeah, you would think, oh, we could oxidize this, but now we have this all conjugated. So remember, this is electron withdrawing. So what's happened? Actually, this is in a conjugated system. And the most reactive part is actually over here, right? This would be being pulled in this direction, it's conjugated. And so actually what we're going to use is a reductase, okay, that is going to effectively add a hydride right here. These electrons are going to shift this way, and we're going to insert a new bond. So this will shift here, this would shift over here, and it would actually pick up a proton. So picks up a proton. Where? Protons all over, from the protein. And what's going to happen is our NADH that provides it is going to put a hydride here. So what happens? And it will make a cis bond. Here's our alpha. Now here's our beta. And then we just continue how many are left. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And this looks exactly like if we had just a normal monounsaturated. We get our cis bond here. Now we just use our isomerase, flip it over. So now we just do our isomerase. We'll flip it over between the alpha and the beta. And then now we can just do steps 3 through 4. And that's it. So steps. Does that make sense? So
Wouldn't do two.
well, yeah, it would have, then after it does that one, everything else is like a saturated fatty acid after that. So it would do this, would cut this off, then it would do another set.
Yeah, but you wouldn't use step two. You said step 3 before, but you wouldn't use the one.
Oh, yes, I meant two. Yeah, I'm sorry. I should be two. I was skipping step 1, but for some reason I was counting that as step 2. Yes, like that. And then it would oxidize here, and then we would have 2 more rounds to do to finish it up. Yes.
On this step, right after you add back, I don't know what step that is.
Which one?
That, well, can you do an NAD and NAD, like a reductase reaction that
This-
gets you to the next step where you're using an isom instead of?
So,
I'll show you on here.
huh?
Because on here you did a different step. You did a reductase using NAD and NADH. So you skip that step, and then it goes straight to where you can do an isomerase.
What?
So,
So this is the reduction step right here. Okay, in the original one that I posted,
yeah.
I didn't do this first.
Okay.
You have to do this first.
So you do have to do that first?
Yes.
Okay.
And then I went back in, I haven't posted those. But you have to do this first to get this conjugated.
Okay.
And then you do this. What I originally did was I bypassed this and said, well, you just do this step, right? But it doesn't allow it to be as reactive.
Okay.
So You have to do step 1 first after that. I'll make sure to post those updated slides. Because you missed that, didn't you? No. All right, so that's the difference. If you just had one monounsaturated fatty acid, you know, you wouldn't have to do all the flipping around. You wouldn't have to use this one. You would just use the isomerase, and the isomerase would finish everything up for you. Now, don't miss the main points here. Because there are fewer electrons, right? Because with the unsaturated ones, you have double bonds, there's less energy, right? Because you skip at least one time right here, you skipped step 1. Step 1 usually provides you with reduced cofactors. And remember where these all go to. I'll do it in a different color. Remember that this gets shuttled to E transport chain, right? And as well as these can be sent to complex 1, right? So as you get more degrees of unsaturation, you actually have less energy because it has fewer electrons. Is there anything else that I wanted to talk about? No. Are you okay with just me doing that? Instead of a monounsaturated, you basically just would start from here, and imagine that that's not even there. So start from here. If that wasn't there, you would do this step. And once you got to here, you wouldn't even have any unsaturated fatty acid. You would just go from here like normal beta oxidation. So we'll just kill 2 birds with 1 stone. Okay. Is everybody, we're not going to kill anything, I hope. Is everybody okay with that? Okay, so that's basically what we went over, and the ultimate purpose of this, right, is to make acetyl-CoA, which is coming off here. And remember where we're going to send that as well? To citric acid cycle. Now I could ask you a question like what, compared to, because you've already done glycolysis, compared to carbohydrates, which has more energy, mass to mass? Carbohydrates or fatty acids? You could answer.
Fatty acids, because
Yep.
it has like the more, I guess, like carbons around.
More electrons, right? It's more reduced. And so we talked about that. So those kinds of things I would expect you to be able to pull out from this as well. Remember, it only takes one step of activation. Use 1 ATP. That's enough to charge this once with coenzyme A. Then after that, it's just a cycle. You don't have to charge it up anymore. Carbohydrates are already partially hydroxylated, right? They're already partially oxygenated, and our whole power that runs the mitochondria and runs and fuels the cell is to siphon off electrons from carbon. But when you bring in carbohydrates first, well, carbohydrates are already partially oxygenated. So in other words, they're partially oxidized. Whereas fatty acids are largely reduced. So you get much more energy from fats than carbohydrates. And also, this is how your body largely stores excess energy as fats, because it has more mass, or it has more energy per mass, and its properties make it useful too. What are its properties? It's fairly hydrophobic, doesn't absorb a lot of water, actually likes to be away from water, so it likes to get packaged up into the adipocytes as kind of a solid fat, okay? Or as these droplets that are largely water devoid. So it makes a lot of sense. Okay. So we're good with that. Okay, so that's basically, we talked about that, and then we talked about the transport of fats, which is an important thing. And I'm also going to lump cholesterol in here. We haven't gotten into the synthesis of this, but that's a really important component too. We'll see that basically cholesterol is the precursor for all your hormones. So people that have, out of whack cholesterol levels usually have out of whack hormone levels as well. And it's all jacked up because you've got this regulatory problem with your cholesterol. But anyway, we'll get into that next time in class, hopefully. So remember, the idea is, well, these are very insoluble. So we need something to deliver them. Therefore, we need delivery. And so fats are really never freely floating. I mean, very small amounts of fatty acids might be freely floating. But largely your fats are locked up into something called what? Lipoproteins. What are they? They're a complex of fat, cholesterol, and proteins, apolipoproteins, they're called. When they're by themselves, when they're in the complex, they're just known as lipoproteins. Okay? That form kind of vesicle structures, micelles. Okay. And we know there's a whole range of these, right? Starting with what's the least dense? What is it?
LDL.
Close. Chylomicrons. Chylomicrons. Right, which have the bile salts and things like that that come in. So these are the least dense. And where do they get their density from? Do you remember? Yep, yep. So the more fat, the less dense, right? Highest amount of triglycerols, or let's just say fatty acids. But when we talk about storage, we're talking about triacylglycerols, right? So it's the least dense, and then we go to very low density lipoproteins, right? Least dense, and we're going over here to the most dense. So very low, and then what's the next one? Do you know what?
VLDL.
We just did the VLDL.
Oh, IDL.
IDL, intermediate, right? Intermediate. Then which one? Everybody loves this one. Low, LDL, low. I'm just gonna put L, low, and then the last one is high, right? And the trend is you go from highest amount of fatty acids to highest protein content. Lower fatty acid content, higher protein content. So that's, fats float beyond water kind of less dense. Okay, now we know that there are different proteins that form these complexes. You don't have to know the specific proteins, but what you want to know is what do those proteins do? So the proteins make up lipoprotein structures. What are some of the things that they do? What do they do? Name one thing that those proteins do. Yep, so they help to deliver fats, so they target, right, where they go, so they can target, say, receptors. When we think about the LDL receptors, right, we talked about that. Number two, they help with processing, right, they float throughout, you know, the capillaries, and they have these proteins on there that are solubilizing it, and they're bringing it in contact with lipases, right? Helping with the breakdown. So they help with breakdown / processing of triacyl glycerols or triglycerides. You know, they often use that in the medical term, the same thing. Breakdown and processing of triglycerols. We think of the lipases, right? They help them to associate with the lipases that help to basically cut them apart from triacylglycerols into the fatty acids so that they're more soluble, can get absorbed into the cells. What else? So we can deliver them, we can target receptors, we can break down, aid in breakdown and processing. We already kind of said solubilize, right? Improve the solubility. There are probably other things that they do that are not coming to my mind right now. But those are the main things. We already talked about targeting. So those are the three main things that they do. And then as they're processed, right, you get different proteins that get associated with them. Maybe in the liver, right, the liver will kick out different kinds of lipoproteins, get delivered, and then as they get broken down, we call the things that they break down into remnants, right? You can have remnants of the chylomicrons, you can have remnants of the very low density lipoproteins, and those get trafficked. What's our main carrier of cholesterol? Which one is the delivery vehicle for cholesterol? LDL. So that's something that's unique about LDL, is this is also our cholesterol deliverer. That's one of its main functions. It delivers triglycerides, but it's also a main transporter of cholesterol. And when they check you to see if you have high cholesterol, they usually check your LDL versus HDL levels. Because the HDL, if you remember the pathway, HDL is what gets kicked out after the LDL has been absorbed and the tissues use it, and then they kick out HDL. So if your HDL is higher than your LDL, that means you're utilizing your cholesterol, right? You're utilizing it efficiently, that's why its levels are low. If it's high relative to the HDL, the idea is you're overproducing cholesterol, either from your diet or your cells are synthesizing way too much, and there's an excess around, and if there's excess around that's not going to get absorbed, it'll start to form plaques, it'll basically precipitate out in your blood vessels, you'll build up plaques, you'll get inflammation, you'll get buildup of fat in there, and eventually you'll have a heart attack, or a stroke or something. Heart disease, right? And so that's what they're looking at. And we'll see cholesterol biosynthesis, we'll do that next. And so you get cholesterol from two sources. I don't think I need to teach you. But anyway, you can get it from your diet and you can get it biosynthetically. You can produce it yourself. Some people can diet all they want and cut out all cholesterol. Their cholesterol will be high because their bodies actually produce too much. Now, some people can eat as much cholesterol as they want to their heart's desire, and their cells will utilize it as efficiently. So they have no reason to really diet and cut down on their cholesterol because their body uses it just fine. So we'll talk about that next time. But this is what's happening here. You've all probably heard of LDL, HDL levels. That's because LDL is the delivery agent for cholesterol. I think that's about all we talked about in the delivery. We talked about the adipocytes as just special tissue for storing up fats. So the fatty acids will get converted into triacylglycerides, and then they'll get stored up in the adipocytes. Mainly that's stored up in the midsection of, the belly section of individuals. There are other sites in the body where that can also be stored. And of course, obesity and things like that is where fat starts getting stored pretty much all over the place, where it should not necessarily be. But in those areas too where the adipocytes are. So the adipocytes are, my understanding is there's a limited number of them and they just get fatter or shrink. So you have a certain number of adipocytes and they just get fat or shrink depending on how much is stored. Similar to your muscle cells. People with big biceps and stuff, you actually have a limited number of muscle cells and they either get thicker as you work out, you build up more muscle protein inside, they either get thicker or they shrink. And if they die, they're basically gone. How do I know? I know a guy in kinesiology and he's working with muscle cancers and he said, oh, I got this muscle cancer, can you make a virus particle that could deliver agents to it? I said, yes, I could. Do you want to kill them? He said, no, I don't want to kill them. Because I always thought it was like you build muscle by getting more cells, right? You work out. He said, no, it's not at all how it works. You build it up, you start with a certain number of cells and they get thicker. And if you kill them off, if you have a muscle cancer, you don't really want to kill the cancer. You don't want to kill those cells. You want to revert them back to normal because you have a limited number of those cells. Kind of cool. You learn something new every day. So anyways, that's how that's said. Okay, cool. And bonus questions from this time are always fair game. So you listen to what I talk about. Yeah. All right. So that's kind of what we've covered, right, with fat metabolism so far. How do we break down fatty acids? How is it stored? How is it delivered? Everybody's writing everything down, right? This could be a bonus now. So that's what we did there. So you guys ready to go through photosynthesis? Okay. Does anybody have any questions about any of that? Yeah, Lisa.
So how far do we go down, like, on the review? Like,
Basically to the fatty acid degradation.
This is where they all.
It's where I boxed in and said, review Monday, right? And I didn't post that yet, did I? Did I? Okay. It's that one, which was basically the summary of all the catabolism. And then today, we started actually doing the anabolic pathway, the building up. We only got into a very little bit, so I'm not going to test you on that here.
Is ketones going to be, or ketone bodies going to be on that?
Yeah, ketone bodies could be on that. Yeah. So beta hydroxybutyrate, acetone. The main thing there is what they're used for. They all come from acetyl-CoA, but the main point there is that you want to realize that they serve as a precursor for acetyl-CoA for the brain. So here's what I would like you to know from those. Ketone bodies. Okay, what are they? Basically, they're produced from acetyl-CoA, get converted into this in the liver. So, acetone as one of those. Beta hydroxybutyrate. 1, 2, 3, 4. beta hydroxybutyrate. You don't have to know the structures, but those are ketone bodies, okay?
Dr. Patterson, what did you write?
Converted into what?
Yeah, I know.
In the liver?
Oh, okay.
I'll rewrite it. Okay.
What you trying?
I'm gonna write it over here, because at the edge is just, my handwriting is in. So this would be from the liver. Okay, acetyl-CoA from the liver gets converted to ketone bodies that are in the liver. And then what happens is, these can be exported to the blood. Okay? And they can go up here. Let's see my attempt at making a brain. Alright, so they go into the blood, up into the brain, and then what happens to those ketone bodies is they get converted back to acetyl-CoA. Okay, and so use as energy when glucose is low. Or not. Okay. If it's me, there's facial hair. If you want to see a picture of me without facial hair, come into my office and see my wedding picture. Anyway. Okay, does that make sense? So that's, and so it makes sense, okay, so let's tie this together. We have no glucose. The liver expends a lot of energy to try to synthesize it, but at some point, it becomes kind of too energy expensive to produce very much glucose. So, where do these come from? Remember, this comes from fats. We're able to take the brain here, which runs on glucose, normally, but we're in conditions of starvation or fasting, and we don't have enough glucose around because our glycogen stores have been released. Our liver's been trying to keep up with gluconeogenesis, but it becomes expensive. And so what does it do? Goes to its fat stores. Oh, let's just take fat and convert it into these ketone bodies that we can take in the blood, or through the blood to the brain, and then the brain will basically start utilizing ketone bodies. They'll be inserted into the citric acid cycle because they get converted into acetyl-CoA. So see how it allows your body to adapt in conditions where there isn't any glucose. And it effectively makes your brain run off of fats, but indirectly. Can't use fat directly. So the liver converts it to ketone bodies that can travel through your blood to your brain. And the brain converts them into acetyl-CoA, which it can run in its mitochondria and keep up with the power needs. Does that make sense? So these are separate pathways, but there's this connection. And even in different tissues use different fuels and can be adapted to use different fuels. Okay. So we cool with ketone bodies? Cool. Rock and roll.
You don't need it.
So, photosynthesis. We got the dark and the light reactions. Let's start with the light. Makes me think of that, I think it's Manfred Mann song. Blinded by the light.
Like a juice, standing in the room and that.
Maybe those aren't the right words, but they haven't come up in my mind.
Oh, there it is.
Does anybody ever do that? Like you think you know the words to a song? I'm just singing anyways.
Sounds like a real version. We do that new song.
All right.
my car and making it work.
So we'll do the light reactions. Photosystem 2. And we have over here cytochrome B6 staff. Complex 3, right? I'm just going to put that in here. We can think of this as complex 3 from electron transport, but it's cytochrome B6 staff. And then we have over here photosystem 1. Just because it was found first, it became photosystem 1. Okay. And we have some intermediate electron carriers, right? So these are the integral membrane proteins. So how I like to remember this is draw those out first and then talk about what factors make them up. What are the pigments that are responsible for doing the electron transfer, okay? So we have what we call the special centers. We have the P680 here, and we have the P700 here. And remember, this is what brings in the light. Right, okay. So that's where we get the light, right? So let me just draw them from here. Here's our light coming in. Light. And of course we have the special center, but then we have all those satellite pigments all around it, right? And they all get dumped into there to provide an energy flow to consistently activate those electrons, and then we can do our electron transfer. But that transfer only comes from the special center, right? Okay. Then we think about our intermediate carriers, okay? We have the P680, we have the P700, we have plastoquinol, which we just call Q. Okay, that's our Q factor. Remember, and this becomes QH2, and then it gets sent over here, and it will send its electrons through here to something we call PC, plastocyan, right? Which is effectively cytochrome C. It's a copper protein. Okay. And then basically this will shuttle electrons, and I'm just drawing out the flow of electrons over here to the P700, and ultimately those will come up and they will get attached to ferredoxin, which is an iron sulfur protein. And ultimately the electrons will go from that to the ferredoxin, NAD, P plus, reductase. I always remember it as FNR, and I'm fine if you just remember it as FNR. Okay? And so this is the flow of the electrons through here. Ultimately, what is our source of electrons? Water. And these are going to be evolved from something we call the oxygen evolving complex of photosystem 2. Right? And what happens here? We're going to have to get one molecule of oxygen, O2. We actually need 2 molecules of water. We got to get 2. So we're going to actually send 4 electrons through this system. Okay? Now, when it splits that, we're going to get 4 protons pumped. And remember, we are putting these in the lumen. And outside here, we have the stroma. Remember, the special structures that these are called thylakoids. They have the thylakoid stacks, and then the innermost part we call the lumen. The outside, the cytosol around the thylakoids, we know those as the stroma. Okay, so we get this. We get our protons stripped off, a strategy that we've seen before, of stripping things off to pump protons. And ultimately, we're going to send 4 electrons through here. So we're going to send 4 electrons over here. Okay? That means we're going to get 2 of these. All right? Because each Q will hold 2 electrons. So just gonna draw this out. I'm fine if you just put 4 electrons once, okay? Now, remember, this is equivalent to complex 3, so this does that Q cycle. Remember that Q cycle here? So this is where we're going to do our Q cycle. So for every electron we put through there, we get 2 protons pumped, twice as many. And I know I messed up the stoichiometry in class on this, so we're sending in 4 electrons, right? 2 QH2. So for every 1 electron, remember the Q cycle doubles it. So we send 4 electrons through, we pump 8 protons from 2 bars. Okay. We send this over. This complex isn't doing anything, it's just pumping electrons, right, up through. Ultimately, those electrons go to ferredoxin, that's an iron sulfur protein, over here to the ferredoxin NAD plus reductase. And ultimately, what we're going to get out over here, we get NAD plus coming in, and NADH coming out. And for 4 electrons, you would need 2, right? Because each one accepts 2. And so what we're ultimately doing here is we're building up protons in the lumen. And this is for a purpose, and I'll extend my thylakoid here. Oops. I wonder where people come up with these names like thylakoid, strontium. Maybe make it up anyway. We come over here and we have our little ATP synthase with our bell pepper, right? Which is known as complex 5 in the electron transport gene, but we have ATP synthase. Think about how that looks. I'm not an art critic. Yes, I am. Not going to post myself. Okay. And then what happens? We send all of these over through here, right? And then this powers ATP synthase so that we get ATP out. Cool. And that's what the light reaction is all about, right? We've gotten things that we really need for the dark reactions. So we get our ATP, we get our reduced cofactors. We also talked about a pathway where if you run out of NADP+, you've been sending so much through this pathway, which can happen during the day when you get intense sunlight. What can happen? Remember that this ferredoxin can actually cycle it back here and pump protons. Do you remember that? That there is a off cycle, off pathway. So if this is blocked over here, so let's say this concentration gets low, what happens is this can shuttle these back to the Q site, basically back to cytochrome B6F, and basically can pump protons. Do you remember that? You can shuttle electrons can be used for pumping protons. And then you can have that cyclic cycle, electron cycle. But that's only basically if, you know, we don't have enough of this around. Do you remember me talking about that, where you can shuttle electrons back through cytochrome B6F and it will pump protons, so follow the green. Okay, it can shuttle these back through and you can pump protons back that way. Do you guys remember that? And that was a way of, if we lack these reduced cofactors because we have so much, we can still make the lumen have a very low pH, and it will be used to make ATP. So what I'm showing here is if NADP plus concentration is low, can cycle electrons through B6F and pump protons to synthesize ATP. So remember, we have that release valve so that we can continually produce ATP if we're getting low. So no matter what, whether we have this around or enough of this around or not, we can continually run electrons through this pathway, and we can get proton buildup. And so that's an alternate cyclic path. You all good with that? That was one that we talked about. We didn't really draw it out, but. Okay, so that's our light reactions, and that's basically everything we talked about. I compared it in the slides to the electron transport chain, and basically if you look at all this, this is exactly the reverse of the electron transport chain that we see in the mitochondria. And in order to go in reverse, what do you have to do? You have to get energy from somewhere else. We get it from the light. So this is using light to force the electrons to be excited to do electron transfer through this electron transport chain that effectively goes in the reverse of what the electron transport chain in the mitochondria would run. Electron transport chain in the mitochondria would start with reduced cofactor and go the other way, based off of reduction. So that's a kind of a key theme that we saw, and I spent quite a bit of time talking about. Okay, so we good with the light reactions. Okay, dark reactions. You start with ribulose 5-phosphate, which you've seen already, pentose phosphate tablet. And if you look at all these intermediates, you've already seen in glycolysis. They're just being reused in a different way for a different purpose. So you get ribulose 5-phosphate. And this is where your ATP molecules come in from the light reactions. So I'm just going to put it once, ribulose 5, yeah. Okay. And then those ATPs, we'll need 6 of these, okay? Because we need to fix 6 carbons to be the equivalent of glucose, right? One glucose molecule has 6 carbons, so we're going to have to fix 6 CO2 molecules to get a net gain of 1 glucose. But all the carbons don't go to the same molecule. They spread out on several molecules, but we get the net gain. It's about net, how much we get. So here, we're going to send in 6 ATPs. We get 6 ADPs out. Remember, these came from the light reaction. Okay, now we're going to make ribulose 1,6. Or sorry, 1,5. 6. 1, 2, 3, 4. Everything the same. Okay? And this is the committed step. This is the one that controls it, is the next one, which is Rubisco. Here's where our Rubisco comes in. And Rubisco, remember, we'll bring in 6 CO2 molecules. It'll also use 6 H2O molecules, so here's where your water also comes in. Water is used as an electron source, it's also used here. And Rubisco, right? Rubisco is going to carboxylate, and I'm not going to draw it out. You don't have to separate it like I showed you in class, where I had 2 different pools. But what happens is the CO2 gets added to this carbon, and this gets cut in 2, and we make 12 phosphoglycerates. So 3 phosphoglycerate. And if I'm not putting hydrogens on, they're assumed to be there, okay? So we've already seen this one. 3 phosphoglycerate. We saw it in glycolysis. Okay? And if you look, part of this pathway is out of glycolysis. It's the reverse. Okay? So Rubisco attached those CO2 molecules. Now we have 12 of these. And here's what you want to remember. In glycolysis, or gluconeogenesis, what do we make fructose from? You remember? Dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, right? Remember that? Step 4, right? Use aldolase to make fructose, okay? And that's essentially what we're doing. We're starting here and saying, how do we get back to fructose, which can be converted to glucose from here? We just have to add 2 3-carbon molecules of glyceraldehyde, being 1, and dihydroxyacetone phosphate. So effectively, from here on out, we're trying to get glyceraldehyde 3-phosphate because that's the one that can be used by aldolase to make fructose, which can be converted into glucose. So we started there. Next step, we're going to bring in some ATP. Okay, we need 12. It's expensive to synthesize glucose. We get 12 ADPs out. And then what we do is we make 1,3 bisphosphoglycerate. And then the next step is we want to convert this into glyceraldehyde. This is actually the reverse step of what glyceraldehyde dehydrogenase does in gluconeogenesis. So here we're going to bring in NAD pHs that we got from the like reactions. We need 12 of those. We give up those electrons. And now what we do, and we give up the inorganic phosphate that was attached here. And we're going to make glyceraldehyde 3-phosphate. P3P, right? That we've seen before. And we're going to make 12 of these. And then effectively, oh, hey, we can make now glucose from this, right? So these are the steps that you want, right? And we know we could say, take some of these, and effectively, we can make fructose from these, and fructose we can convert into glucose, right? Think. Those are the reactions that I want you to know. But these are all intermediates of gluconeogenesis. From after that step, this is found in gluconeogenesis and glycolysis. Okay? This is 2, and this is 2. And so what happens here is the cell here, the chloroplasts, are using components of the pentose phosphate pathway over here and kind of intermixing them with reactions of gluconeogenesis, but inserting a new reaction here that bypasses and makes something unique, integrates the two together. It's kind of cool. I know I probably don't need to talk this much about it, but it's interesting. And of course, some of the fructose goes back this way through a reverse pentose phosphate pathway. And then we get out our net gain of 1 glucose, okay, through that way. So that's the main part that I want you to see is, can you do, these are the unique reaction steps to getting to glucose. We ultimately want to get to glyceraldehyde 3-phosphate because that's the same thing that we use in glycolysis, right? Same thing, same thing. So as you're looking through these, hopefully you're seeing these themes. You'll box these in from the light reaction. But remember, this is also the precursor in gluconeogenesis for fructose, which gets converted into glucose. So it's pulling actually reactions, similar reactions from other pathways to get there. Does that make sense though? And that's why, we start with glycolysis, very well understood, and then you start seeing, oh, there's components. This is straight out of gluconeogenesis and glycolysis. All this is. Yeah, you're throwing in NADP cofactors, okay, but all that is, go back and look at your glycolysis. That's straight out of there. It's like chunked out from it and put into this new pathway. Everything over here is basically the reverse of the pentose phosphate pathway, and you get ribulose 5-phosphate. So you're just chunking 2 different kinds of pathways together. I'm sorry, I'm talking too much. I feel like this is my time where I've already gone through it and we can talk a little deeper about this. So that's the dark reactions. Rubisco is the main, right? This is the step that really matters, and this is the step that's regulated. So now, just because these are called the dark reactions doesn't mean that they occur in the dark very well. What it means is, to do these reactions, it does not require light. All of our components from this, they were generated from maybe the light reactions, but light isn't directly needed. So that's why they call it the dark reactions. But actually the dark reactions are stimulated, or you could think of regulated, by light. So while this is the dark reaction, this process is actually regulated by light. And it's regulated at Rubisco. Okay? So, I'm going to go to the next slide and we'll talk about regulation of Rubisco. You got everything down okay? Okay. Oh. I'll put another slide. Used to be a song, go slide, slide, slippery slide. You know that? From John Harris, back in the day. Okay. So, regulation of Rubisco. So here we have fixing CO2. There's our substrate. substrate here, 1, 2, 3, 4, 5. Is we make phosphoglycerate. Why am I doing this? Just to bang it into your heads. That's all. The more you see it, the better off you are. So what is regulating these? One of the things is high pH. Put this in. So high pH activates. Now I'm going to delve into this a little bit more. Remember, Rubisco is in the stroma. Right? So it's in the stroma. Stroma gets more basic as light reactions are active, right? Because the light reactions, what do? They pump protons into the lumen. So protons are taken from the stroma and pumped into the lumen. So the stroma pH increases during light reaction. That makes sense, right? So, and then Rubisco gets more activated. It likes basic conditions. So you can think of how it's deprotonating the protein, making it now more active, okay? Because it's sensitive to the protonation state of the enzyme. So, pH increase activates. When's that going to happen? When the light reactions are on. So while this process does not need light, the enzyme requires that the light reactions are at least going to make it more active. When it gets dark, what happens? This process is going to shut down. Rubisco is going to slow down because it's not going to have as much substrate coming to it, right? It's not going to do that. Okay. The other thing is an increase in magnesium 2+ activates Rubisco. And this is because as H+ is pulled out, Mg2+ migrates into the stroma. Counterbalance. So it's losing all these positive charges, but it needs to try to neutralize that so it's not so out of balance. It brings in magnesium, which is not protons, but it is a positively charged ion that will help counterbalance that shift of protons. Okay, so that moves in there to try to, mediate that disparity in between the positive charges. Okay. The other thing that happens here that activates this is there is an enzyme called activase. Okay? Activase helps remove inhibitors of Rubisco. And there are actually several inhibitors of this, but the one we talked about was the C1AP, I think is what it's called. C1AP. That's one of them. And what the activase does is it takes things like this and it opens the active site to remove inhibitors. That's what that activase does. So these inhibitors get in there, they mimic kind of the substrate, and sometimes they're the product. The product can actually inhibit it. And then what happens is it gets stuck. So Activase can come in and basically open up the active site of Rubisco so these things can diffuse out. Now, Rubisco is controlled, or Activase is actually related to electrons. So there's a reduction pathway that is controlled by ferredoxin, which we saw, right? Ferredoxin, we saw that in those light pathways. And ultimately, ferredoxin shuttles its electrons through a pathway that leads to activase. There are intermediates of this. And so what activates the activase? Electrons from ferredoxin. So ultimately, where are we getting those from? From the light reaction. So activase is actually regulated by electrons from light reactions, right? Because here's where those electrons come from. So activase gets activated by becoming reduced. So activase activated by being reduced. And it has styles that are important to get reduced. So there are inhibitors, and it's the objective of the activase to do this. So you have inhibitors, but I'm putting those together with the activase here because they don't get removed till the activase comes over, opens it up. Then when these inhibitors get removed, they get broken down, basically. There are enzymes around that'll break them down. So they get removed from the active site, moves the inhibitors, and then they get broken down. So this one actually gets dephosphorylated, and it can't act as an inhibitor anymore. So that's how that whole process is regulated. So it doesn't require the light reactions to do anything except provide those precursors, but it's stimulated by the light because it influences all the chemical environment that's necessary to make Rubisco more active. So at night, what would happen? You have these inhibitors that would get bound up in Rubisco and it wouldn't be active because the inhibitors are bound. Then as you start to get light in the morning, what happens? Well, we start to change the pH, start to change the magnesium. We get electrons flowing back through that again. And then the activase gets activated, comes over, opens up Rubisco. This inhibitor gets expelled out, and then it gets broken down. And now we've got everything going again. It's like turning the switch on in the morning at a factory. Oh, it's been off. Let's start getting everything going. That's the switch. The light's the switch. It doesn't require the light, but the light gets everything going. Regulates that whole process. And that's it. I didn't think we would take all that much time, but we did pretty good. Does anybody have any questions about that? Do you guys like